In this screencast, we're going to start examining and interpreting kinematics in the polar frame. And so we're going to start out by looking at the velocity expression. And in the velocity expression for the inertial velocity, we have r dot in the ER direction plus r theta dot in the E theta direction. Now, I understand that the r's and the theta dots and this kind of strange basis that we're working in is a little bit intimidating, particularly when we get to the acceleration. But we're going to walk step by step so that we understand each of the terms and that we interpret each of the terms so that they have physical meaning. So let's look first at a case study of a circular path around point O. And here we have a particle P, which is rotating, and we'll go counterclockwise because that's typically our positive direction of rotation. But point P is rotating counterclockwise about point O. And so first let's define the velocity vector at this time t that we see our point P. So to do that we need to define our position vector, which is r of P with respect to O at time t. And remember that point P is going to be moving counterclockwise around the circle. So that means that at some point in the future, it'll be over here, and this can be r of P with respect to O at time t plus delta t. And so using what we have on these positions, let's create a velocity vector. And so we're trying to find the velocity at time t, which is when point P is at this location. And so by definition of this derivative, it's going to be the limit as delta t approaches 0. So it's going to be, when this secondary point, t plus delta t, is close to point P. And so this gives us a vector of the point P moving in this direction. And this is the velocity of point P with respect to O as observed in the inertial reference frame. And keep in mind here that this velocity vector is a vector, so meaning that it has both a magnitude and a direction. The magnitude we typically express with the length of the vector that we draw, and then its direction, being up and to the left, indicates that we have a counterclockwise moving particle around this circle. If it were moving clockwise, it would be pointed in the opposite direction. So now let's add a polar frame to this particle. So here we see the polar frame B, which is defined by three basis vectors, ER, E theta, and then EZ, that are all perpendicular to each other. ER is defined as in the direction from O to P. We have EZ, which is pointing out of the page, and then E theta, which is the cross product of EZ and ER. Now that we've defined our polar frame in this particular situation with a circular path of point P around point O, then let's interpret our expression. The inertial velocity of P with respect to O is equal to r dot in the ER direction plus r theta dot in the E theta direction. And so being on a circular path, we know that the radius doesn't change. If the radius doesn't change, then that means that r dot is equal to 0. And so going back up to our velocity expression, if r dot is equal to 0, then our first term doesn't exist, meaning that there is no velocity in the ER direction. And so physically, when we look at our trajectory of our point P around this circular arc, then r dot is equal to 0 says that we have a constant radius, and there is no velocity at this point in time along this direction, which is the ER direction. And so it follows that all of our speed is in the E theta direction, which is perpendicular to ER. And so that speed in the E theta direction is, the magnitude is r theta dot. So in this situation, the velocity of P with respect to O, as observed in the inertial reference frame, if we take the magnitude of this, then that's equal to r theta dot. And you probably also recall from physics or other courses that the velocity is always going to be tangent to the path of a particle. And this is true in this circular path that we see here, but it's true for all paths where the velocity defines the path because it's always tangent to the path. And this is going to come up in future screencasts when we introduce a path frame. And of course we know that most motion doesn't occur in a circle, so we need to be able to deal with when we have an ER component for this velocity. So let's examine when r dot is not equal to 0 using the polar frame. And so a common way to make sense of this is by looking at a spiral. And what's happening in the spiral is that we're starting with the particle P at point O, but then as we sweep around this angle, the distance is getting further and further away from the origin, which means that r dot is a positive value. And so let's draw that component where we have r dot in the ER direction. And so now consider what this term is telling us, is that we have motion of the particle in the ER direction. So if we go back here to our expression for our inertial velocity, and we have r theta dot in the e theta direction equal to 0, so no component in the e theta direction, then we only have a particle that's moving out or moving in. So this would be the radial velocity. Or another way to say it is the speed in the radial direction, e sub r. And now let's add our e theta component. And so we know that the magnitude in e theta is r theta dot. And we saw above that this is the speed that's tangent to the radius away from the point in which we're referencing. So now that we have both of our components drawn onto our page, we can look at the resultant, which is our velocity of p with respect to O as observed in the inertial reference frame. And you can see that the velocity vector, is tangential to the path. So it's along the path at this particular point, and then it's going to be along the path at all points. And so let's spend just a moment gaining a little bit of intuition on the magnitudes in the ER direction and the E theta direction. The r theta dot, as drawn here, is a much longer length, a higher value than the r dot term. And I think you can see this here on the path, because in the path of this spiral, we're making it around theta, or around to rotate around point O faster than the r dot term, which would be pushing it out of the radius, which is going to make this more of a flatter spiral with a gradually increasing radius. Now if you flip the two and make the r dot term larger than the r theta dot term, then our spiral would take off at a faster rate away from point O than it would be in its attempt to curve around and match that circular form that we saw in the last example.